We're going to get the evening session started. So our first speaker is Frank Nothaft. He's a second-year PhD student in the AMP Lab. He's doing some very cool stuff. He has backgrounds in systems, but he's quickly become an expert in genomics. And he's going to be talking about some of the really cool stuff he's been building for genomics on top of Spark.
Thank you very much for the introduction to me. As introduced, I'm Frank Nothaft. Today I'll be talking about Atom. So Atom's a system that we've been working on in the AMP Lab for the course of the past year and a half or so, with many collaborators, a few of whom are actually in the audience today. So it's a cross-institutional project, and we've been really lucky to benefit from a lot of good help from both other people in the systems community as well as people on the bio side. Just to motivate this problem, there's this one slide that always comes up at every single bio conference that you go to that is exactly this slide right here that's showing how the cost of sequencing a genome has dropped over the course of the past 15 years. So in 2001 was really when the Human Genome Project, as well as a few associated projects were really kicking off and going through their peak. They weren't kicking off. Sorry, they weren't kicking off. They were going, they were kind of peaking, and just having that project go to completion and finish has really kicked off a lot of innovation in biotechnology. So one of the big things that's happened is, we've gone from it costing about $1 billion to sequence a genome down to the point where right now, this was just announced a few months ago, we can now sequence a human genome for under $1,000. As a result of this, the amount of data that we've been processing, and the amount of data that we will start to process over the next few years is just growing exponentially. There's a few years ago, there was a project called the 1,000 Genome Project. Right now, we're looking at projects that are going to be processing about 4 orders of magnitude more data. There's a 100,000 genome project that's kicking off right now. So one of the big things that we realized about a year and a half ago is this big increase in genomic data has it's coincided with this trend in computer systems where we've been building systems to process really large data sets. So we actually overlaid some of these these big dates in both genomics as well as big data technologies on this sequencing graph, and amusingly enough, they actually line up very well. So we think that it's a really good, Spark is a really good technology to use to both process more genomic data. It's a great technology for aggregating data, as well as a technology for processing the data sets that we have right now, but quicker. So I expect that there aren't going to be that many people here who are familiar with with genomics. So I'll start out by taking you all through a brief walkthrough of what we're doing in genomics and what some of the processing that we're interested in is. And what we're looking at here at Berkeley is this process we call variant calling. So what we're trying to do, if you think of your genome, what it looks like is it's kind of a set of books. You have a single book per chromosome. And that book is just a long series of, it's a long string. It's the letters A, C, T, G in some permutation, repeating for about 300 million bases on, or 250 million bases on chromosome 1, down to 50 bases on the Y chromosome, for example. So you have 23 chromosomes as well. We have 2 copies of 23 chromosomes, so 46 chromosomes in total for a human. And when we sequence, what we're going ahead and doing is we're taking these long chromosomes, we're chopping them up into short strings, and then we're trying to say, hey, can we go ahead and reassemble this long string that we have from these short fragments that we've gotten? And when we talk about big data, genomics is one of the is really an area where we truly have big data. Each sequencing run that we talk about, when we go ahead, we cut up your chromosomes into these short fragments, we collect the data, that generates somewhere between 100 and 300 gigabytes of just raw, unprocessed sequence data. What we want to do with this is not just process a single sample. We'd actually really love to aggregate, at the very least tens, but ideally thousands, and maybe even up to 100,000 samples together at the same time, because this gives us the statistical power to say, hey, there's a consistent variation that, let's say people with diabetes or people with Alzheimer's have, and then that allows us to associate events that happen in the genome with actual diseases. So, the goal of doing this processing is, one, to make it easier for us to pull out what these changes are, and then two, to associate them with these, these broader, these non-genomic things that are happening, these diseases or some presentation of a characteristic in a human or in a mouse. Additionally, one of the current problems that we have, even if you look at a clinical setting, you go to the doctor, let's say, maybe you or someone you love has cancer, they go to the doctor says, I'd like to sequence your genome, maybe we can find out some more information about what's causing your cancer, find a better treatment for it. Currently, if I was going to run that processing on just your genome, it takes about 170 hours end to end to do that processing. So, there's a lot of diseases that we can think of where we'd like to take that time and shorten it down as much as possible. So, just kind of talking about this, so how are we actually doing this processing? We've gone ahead and we've said, hey, we're taking these chromosomes, we're chopping them up into these short reads, and then we're reconstructing them. What does that actually mean? So really, what we're trying to do is we're trying to find, like we talked about, we had this human genome project earlier, that did this big bootstrapping. It said, hey, we've gone ahead, we've looked at these people, we've spent a lot of money to figure out exactly what the structure of their genomes look like to try to put together a map of the human genome, so to speak. From here, what we can do is we can try to say, well, we know as a prior that you are going to be the same as every other human being out there at the vast majority of places. You, me, everyone in this room, we're similar at about 999 out of every 1,000 places in the genome. So with that, what we're trying to do is we're trying to take these little fragments, map them back to this map that we have of the genome, and figure out where each one of us is different. So, really, this whole 170 hours that we're spending is just doing a really, really high-quality diff on these, collections of short strings. So the way that we start by doing this is that we want to take the reads and align them back to the reference genome. And this is actually a very computationally expensive process because you wind up having to do some sort of rigorous indexing technique to find a way so that you can map everything to every, you can find, hey, where did this read originate from? Oh, if it has a difference or if it has an error, did it originate from site A or site B, which looks a lot like site A? So it's really this process of going through and just read by read, snapping the read to the genome. After we've done this alignment step, this alignment step right now, takes somewhere on the order of tens of hours to run. The fastest technique right now is actually another technique from the Berkeley lab. It's not MapReduce based, but it runs in about 2 hours. Traditional techniques have run, in the order of 10 to 40 hours. After we go ahead and do this, we then have to actually take the reads that we have at every site and then assemble them down into some sort of a consensus sequence. So, here we're really lucky, all the words on the top match all the words that we've aligned. So we can just go ahead and flatten the reads down, so to speak. In reality, these reads have errors. So, for example, when I sequenced this worst of times substring right here, maybe I missaw, I saw an O, but it was actually an E, or maybe that W was actually a V when I read it. So, there's some error in the sequence that we get. Additionally, there could be just an error, there could be a change, like a true change in your genome. So, maybe instead of, in my genome, I'm an optimist, so maybe I don't have, it was the best of times, it was the worst of times. Maybe I have, it was the best of times, it was the best of times. So what we're looking for are ways that we can pull out, one, so we can discard statistical errors, and then two, so that we can include things that are different from this reference genome, but that are truly apparent in our genome. And so what Adam does is actually, Adam works on this intermediate stage between this first step, this alignment step, and then the second variant calling or assembly step that does a lot of the cleaning up and processing of the reads to eliminate a lot of these errors. These errors tend to be highly statistically correlated, and we run a lot of very expensive algorithms that are actually trivially parallel to do this cleaning. So right now in this 120 to 170 hour process, we spend between 3 and 40 hours doing alignment, and somewhere between 2 and 60 hours doing variant calling. And right now it takes about 100 hours to do these steps that are outlined in red right now. So we said, hey, these are the really expensive steps. Let's focus here. So this then gets down to the question of how do we go ahead and take these steps and make them fast? How do we scale them out? There's a few people who have gone ahead and made kind of naive, well, not naive in a bad sense, but they've made unoptimized approaches to use Hadoop or something to process all of the sites in a genome in parallel. And this is good. This gives us a lot of, this does give us a good speed up, but there are some limitations because of how you would naively partition the reads. Maybe you say, hey, I have 23 copies of my or I have 23 chromosomes in total. Maybe I'll just partition by chromosome. Then I can only divide my processing across 23 machines. If I have this 100-hour-long process, that's good. That gets me down to 4 hours. But you could imagine reasons that you would want to cut the time down further. So we started looking at this in detail. We did some profiling, and one of the first things that we found is that right now the current pipelines are they're limited strictly by I/O bandwidth. You have these 250 gigabyte files. Between every stage of your processing, you've been traditionally doing a read followed by a write. So one of the great things with Spark, hey, we can solve this by caching the data in memory. We don't have to go to disk after every stage. Additionally, all of these algorithms that we're running are parallel in some way. A lot of them, for example, this graph or this assembly problem we were looking at, that is actually expressed as an operation on a specific sort of graph for sequences. So this has a nice implementation in GraphX. A lot of these pre-processing algorithms that we're doing in Atom are actually looking at every single location in the genome in parallel. So it's very trivial to decompose them into a parallel representation. Additionally, as we were saying earlier, we're doing a lot of I/O in between these pipeline stages. Since genomics is really heavy on pipelining and on iterating, we have maybe some EM algorithms that we're running iteratively. We have these stages that we're running back to back. This is just another really good sign that we had a good chance to use Spark to speed things up. So I'll be walking through in the next few slides just some of the general principles that we had. Some of them are more coupled to genomics. Some of them are more coupled to how you can use Spark to process scientific data. And then others of them are just more general principles that I think a lot of us can take and use in the applications that we're developing right now. So the first thing that we went ahead and did in Atom was we actually decomposed the system into a stack. So everybody who comes from the networking side of the world is familiar, with the stack model and the OSI stack or the stack that IP and TCP live in. One of the great things with these stacks is that you're able to decompose problems strictly into layers. Once we decompose things into a layer, one, obviously Spark, where we delegate all of the kind of the MapReduce and up tasks into Spark. But we're actually able to delegate things like our data representation or the way that we define schemas into existing highly performant open source projects. So we wound up building our data schemas in Apache Avro, which provides us with both a nice literate programming framework that I'll talk about later, as well as efficient serialization. And then we've been we've moved a lot of our we've moved all of our storage into Parquet, which you heard about earlier today during the Spark SQL talk. Our general approach has been that we want to minimize data movement. So some of the work that we've done is focused on how do we go ahead and push computing to the data. So we've done a lot of work actually in Parquet, so that we can minimize I/O traffic and minimize just minimize data movement when we're loading. we've also done a good amount of work on the genomic algorithms themselves so that we can try to minimize shuffle traffic between stages or just improve the way that we're actually processing and churning over data. And one of the first things that we ran across, and actually one of the big reasons we've gone for this stack model, is that we're trying to achieve data independence. So one thing that's common in a lot of current genomic algorithms is they say, hey, I have these chromosomes. I'm just going to assume that all of my data is in perfectly sorted order. So it comes, chromosome 1, position 0, position 1, position 2, position 3, and I walk over my data like that. This actually makes it difficult to write parallel code because, one, you have to do a lot inside your parallel system to manage how exactly the data is stored. It kind of it prevents you from doing some things if you have a partition where, hey, if my partition 1 ends and I had position 1000 at the end of that, what happens if I have a sequence that hangs over? Do I have to do something special to take care of the overlap? So one, we said, hey, we're not going to assume this sorted order when we write any of our algorithms. We're going to put this narrow waist, the schema in. We're going to separate ourselves from the way that we store our data on disk. And then we've done actually a few tricks at the programming level. So we've gone ahead and added some things on top of Spark where we're saying, hey, this coordinate system-driven processing, we can just think of that as a join. We come from a data processing perspective. We know how to make joins fast. So we've done a lot of work at the Spark level, and we have that in our repository. So if operating on sorted data or data in a coordinate system sounds like something that you'd like to make fast, that might be something that's worth checking out. Additionally, when we look at the way that we're storing and representing data, so we have a very flat, fully denormalized schema for our data. So this is the schema for the reads that we have. So this is every single little fragment of genomic data is stored in one copy of these schemas. So one of the things that's really common in genomics is that we're making a lot of access to metadata about the read. We might be looking, hey, who did this read come from? Where did it come from on the genome? What is the structure of the genome where I've said that this read is aligned? In current systems, one of the big overheads is that they have this metadata stored in a centralized location because for them they're using a row-oriented store. Having the centralized way, the centralized position for data allows them to one, eliminate any duplication of that. But then they have to make all these centralized accesses to the metadata. So we're using a columnar representation for our data underneath this. So any metadata that's replicated, actually, we're having run length encoding or some dictionary encoding on disk. So we pay very little overhead for storing it on disk. We've done some work inside of Parquet so that we can actually also reduce the memory overhead that we pay once we pull the data off of disk and have it sitting in memory. And this has given us a big performance improvement for some algorithms because now instead of having to go make this centralized lookup, we're doing a local access, and we pay almost no latency to identify the metadata that's associated with the read that we're looking at. Additionally, one of the things that you may note is that all of our fields, even though they have a type, maybe for example, my sequence is a string, they also have they can be set to null. So this allows us to do arbitrary projections on the data. So there's one job where we only look at 5 of the fields in our schema, for example. We're able to say, hey, we're only going to look at these 5 fields. These are going to be the only fields that we project. Since we have a columnar store, it's easy to read only those fields. And our performance is about 10x better because we're doing some negligible fraction of I/O compared to what we would normally do if we were pulling all of the data off disk. And in the end, that's all actually enabled by Parquet. So Parquet is based on, it's an Apache Software Foundation incubator project. It's based on top of Google's Dremel store, and it's a high-performance columnar store. I believe they spoke a little bit about it during Spark SQL today. But the big things that are interesting about it is, one, it supports any projection of data that you want. So if I have this schema that has 33 fields and I only want to look at 10. I only read those 10 fields. Additionally, it has very good support for compression. We get things like run length encoding, delta encoding, dictionary encoding, all for free. So when we look at our schema versus the current file format that people are using, even though they have a compressed file format, we're actually about 25% smaller on disk. Even though we've gone ahead and we fully denormalized our schema, we're replicating the metadata with every single record. So we've been able to get a nicer programming model where we don't have to do this lookup of metadata in some central header, and we've actually improved our space on disk by about 25%, which is nice. Additionally, it's highly parallel, so it's nice. It takes advantage of HDFS just like any other file, any HDFS-based system out there. But when we compare to HDFS-based implementations of the current genomics file format, we do find that we're getting a lot better performance just reading bytes off of disk. So it's pretty efficient, and we're definitely benefiting a lot from using it. And one of the things that's been an interesting project that we've taken on is, so one of the problems in genomics, so, for example, there's this big project out there called the Cancer Genome Atlas. And this project looks at about, a wide range of different cancers. For example, it looks at acute myeloid leukemia and colon cancer. And, it's just a very broad range of cancers. And it's been designed to aggregate all this data together so that researchers, whether they're a cancer researcher or someone like us who works on these bioinformatics methods, they have a way to access this data, and it's very high quality data. It's well curated. However, this is a really huge data set. It's about 40 terabytes, and especially if I'm a researcher, say working on just leukemia, I only want to look at the 4 terabytes that are associated with leukemia. So what do I do? Do I manually pull all the data to myself? Do I have this large cluster that I keep all 40 terabytes on that I share with all the other cancer researchers? How does this work? What we've gone ahead and done, and this was based off of experience from one of our collaborators who was at a big lab in Boston that had this exact problem where they had a large shared cluster. They had a big block store where they were keeping most of the data, and then they were kind of demand fetching it. We went ahead and said, well, one of the great things with Parquet is that it's giving us access to these push down predicates, and it's giving us access to these projections. But the naive implementation that we have for accessing data that is in a block store, whether it's S3 or some other block store that we can access over the network, we can't actually make use of those projections. We can't push down our predicates into the code. So we've gone ahead and we're building, we have it somewhere about 85 to 95% complete, a system that allows us to run a Parquet store on top of S3 and still make full use of push-down predicates and and these projections that we're using pretty heavily in the Atom code base. So if you're also using Parquet, if you're interested in using it on S3, this might be something you're interested in looking at, and we're hoping to close on the feature sometime by the end of this month or early next month. So here's just a link to where that work is sitting right now. When we look at the performance of the system, so we've actually gone ahead. We've done some tests recently where we've scaled up to 128 machines. And when we look at our performance on a single machine versus 128 machines that are actually a lot wimpier, we were able to get about a 130x performance improvement over the current best tool, as well as about I guess we're at about a 64x improvement in performance over our tools on this single beefy node versus 128 medium-sized nodes. So we're very happy with the performance that we're getting. We have linear speed out through 128 nodes on all but one task. There's this one task that you'll notice falls out a bit at the end. That one task that is slowing down a bit when we go to 32, 64, 128 nodes is completing in about a minute at its slowest. So it's a very short task. It's it's not as compute intensive as the other tasks. So there's some bottleneck that we're running into there that we're working on debugging. But point being, we're getting very good horizontal scalability. So we're very pleased with the system right now, and we're just continuing to work on finding other low-hanging performance fruit for debugging, and making sure that our system has as good accuracy as the current best practice systems. And we're glad to say that we've gone ahead and we've benchmarked about 75% of the system against the current best of breed tools, and have even actually found some bugs in the current tools that we've been able to fix. Finally, just talking about the project, I think Adam, like many of the other badass projects, really has benefited from open source collaboration. We're Apache 2, like most of the other projects you've heard about today, and we've benefited from having about 25 contributors across 10 institutions who are pushing to the code base. So that's really driven us along, and it's helped because we come from the software side, other people come from the genomics side, and they've been able to steer us really well, tell us what are some important problems to focus on, and guide us to some good resources. Right now, we're actually working really closely with a new standards organization that's called the Global Alliance for Genomics Health, that wants to use concepts that have come from Adam to change how we do data management and data sharing, as well as how we compute over data in this in the broader genomics field. So I think it's a very exciting time. There's a lot of new changes, a lot of improvement that's going on in the field. And it's kind of unique because when we look at genomics, the cost of sequencing is dropping so fast, and the amount of data that's available is growing so quickly that maybe at this point we've seen 1% of the genomics data that we'll ever see. There's so much more data coming online, so it's a world of great opportunities. So thank you very much for listening to my talk. I'd like to thank many of the collaborators, some of whom are in this room, including one of our open source collaborators who came all the way from Belgium to be here. And I'd be glad to answer any questions that you all may have. Yeah, so the question was, so when we're pushing the data down into S3, are we doing that using Hadoop's S3 compatibility layer versus raw S3 files? So I'm a little less familiar with the exact mechanics of how they're doing it, but from what I understand right now, our collaborators who have been working on this are using the raw HDFS, or sorry, the raw S3 pipes. But I would have to double check that.
So you talked about that you have down to a small number of hours. Is there like an inflection point beyond which the field of this research accelerates? Is it already at like the 1 hour level where genomes interact? Like, what do you think in terms of the actual users of these systems? Is there an inflection point?
Sure. So the question was, so we talked about getting latencies down to an hour. Is there an inflection point at which these tools change how the users are using them? So I think on the read side, it's not necessarily clear whether there's a change from the users. I think it changes the sorts of analysis that you can run, because it makes it easier to run these analyses that are touching many samples in aggregate. On the flip side, when we look, so what we do with the reads is we're trying to take the reads that are kind of this raw data and then process them down into a statistical form that's interesting to the user. What's actually really interesting is looking at that side of the analysis. So right now, this analysis is kind of so this is the big area where people are doing actual ad hoc analysis on top of these what we call variants. And people are doing this with tools that seem kind of crude. They take these text files that these variants come out in. They pass them through GRET. They pass them through CUT. They pass them through SED to do essentially these kind of exploratory analysis on gigabytes of variant information. What we're really excited about is using Atom and using Spark to do this interactive exploration of the variants that you have in one, interactive time, and two, through a a nicer system than the command line. So actually, some of the open source, like some of the people out in the open source community have been working on, actually pulling this variant data in, using MLlib, and using this to do population stratification on interactive timescales, which is not really possible right now. Sure. So the question was, are there any corporate users of Atom right now? I am aware of one organization that is using Atom, but I don't know. Yeah, I'm not sure off the top of my head beyond that one. We're hoping to go to to being production ready in in the realm of the next few months. For these people, they're highly concerned with legacy data formats. Thank you. They're highly concerned with compatibility. Sorry there. The people in industry are very concerned about making sure that we're fully concordant with the current analysis that they're running. So that's our big focus right now, is finding areas where we aren't fully matching them and making sure that we can match it as well as possible.
All right, so let's thank Frank again.